Muy buenas tardes, bienvenidos al ciclo de conferencias nuevamente. Hoy, noviembre 9 del 2021, tendremos la sesión número 9 con el profesor Peter Molnar. Okay, Peter.
Okay, thank you, Hector. So I'm going to continue on this topic of mechanics of large-scale continental deformation. And we discussed the critical wedge and channel flow in the crust last time. So today I'm talking about the thin viscous sheet. And if one looks at a profile of stress, if you like, differential stress with depth through the crust, so the moho would lie here, the brittle upper part, this is where the critical wedge applies, fold and thrust belts, reverse faulting, and the resistance to deformation is dominated by friction. Then one has a weak lower crust, we think, because quartz is a much weaker rock, much weaker mineral than olivine. And so one can have channel flow in the lower crust, channel flow within this region. The thin viscous sheet, we just average everything and look over the entire crust and mantle lithosphere, the entire region in here. And the fundamental problem that has led to this, and problem, I use the word problem to mean difficulty rather than a scientific problem, a question. The forces or the processes that build mountains and that deform continental lithosphere in general must do work of two kinds. They must do work to deform the rock, and therefore do work against viscous or frictional stresses, and they must do work against gravity, which resists mountain building. To build a mountain, you have to lift rock, and to lift rock, you do work against gravity. And I should say that pushing the moho down to make a crustal root also requires work done against gravity, because it's like pushing a balloon down in the water. So the thin viscous sheet and the equations that go with this offer a tool that allows both of these to be included, both resistance from viscous or frictional processes and gravity itself. And the basic assumptions are there are no normal or shear stresses on the top surface, so the wind doesn't contribute to anything and the weight of the atmosphere is negligible. That's an easy assumption to accept. There's no shear stress on the bottom surface of the lithosphere, and hence mantle dynamics applies no basal shear traction. But if you want to include that, this can be added. This is not what I will discuss, but this is not an obstacle if one wants to include it. It's applicable to deformation averaged over horizontal distances comparable to or larger than the thickness of the lithosphere. So the thin viscous sheet is not useful on the scale of a strike-slip fault like the San Andreas Fault. One needs a larger region. And it is also based on the assumption that the vertically averaged properties, the stresses, strain rates, velocities, that these describe regional fields well enough. In other words, the velocity relative to some frame of reference at the top is equal to the velocity at the bottom. Everything is averaged through these. And so once again, one starts with the equation of equilibrium, and that's the equation, but in words, this says that gradients in the stress tensor plus the body force equals zero. There's no acceleration. So this is Newton's second law with no acceleration. And the key steps to applying this are simple. You integrate vertically to get vertical averages. So one averages this equation throughout the lithosphere. Get rid of pressure, because only the deviatoric stresses are the important part of the stress. They're the only parts that contribute to the deformation. Pressure is not, because we assume incompressibility, pressure doesn't contribute to deformation. And usually the rheology is assumed to be of the form where strain rate varies as deviatoric stress to some power n, where n is likely to be 3, could be 1, and it could be 10, but it's a number of that order. And so one has two equations because the vertical has been thrown out. Everything's averaged through the vertical. But when you integrate those, you wind up with equations that look like this, where L is the thickness of the lithosphere, And then one has gradients in the average stresses, the average compressive stress, horizontal compressive stress, the average compressive stress, deviatoric stress in the vertical, average shear stress, and that's equal to gradients in potential energy. This is what makes it really simple. This is the simple aspect. The gravitational potential energy is nothing but the integral of the lithostatic pressure over depth from the lithosphere-asthenosphere boundary to the surface at the top, the air-rock interface. So one has horizontal gradients of the vertically average deviatoric stresses. So left side equal horizontal gradients of gravitational potential energy, which we abbreviate with a capital gamma here. And remember, the potential energy per unit area increases monotonically with mean elevation. Higher regions have larger gravitational potential energy than lower regions. So the nice example is we can do one dimension with the Apennines. It's a very nice study done, published 7 years ago about the Apennines. So this is the Italian peninsula coming through here. This is velocities with respect to the west side, with respect to this side. The yellow circles show velocities very small. I've forgotten they bound, but very small, essentially zero. And the velocities all increase to the right, and they all point to the right. They're all getting faster on this side. So that means this side is diverging from that side. You must have extension in between. If you take the GPS velocities and solve for the strain rates, of course, then you have extension in the middle and through here. Extension, notice this is northeast to the right, southwest to the left. And then the fault plane solutions, the earthquakes show you the same thing. These are showing the normal faulting throughout the high part of the Andes. So the Andes are extending. This is known. The GPS velocity fields are known. But we can look at this in a quantitative way by taking into account the essence of an equation like this. So we're in one dimension, the lithospheric times the horizontal gradient of the compressive stress minus the horizontal gradient of the vertical compressive deviatoric stress plus this shear stress is equal to the gradient in the potential energy. But in this case, we're one dimension. There's no dependence of y, so we can throw that term out. And then we assume incompressibility. So that means that the horizontal compressive strain is minus the vertical compressive strain. If this is extending, then this is compressing, and vice versa. And because the stresses are proportional to the strain rates, we can convert this into a statement that the gradient in the horizontal compressive stress is minus the horizontal gradient in the vertical compressive stress. And these stresses, of course, just depend upon the gradients of the velocity times a viscosity. Here we're being very simple with a Newtonian viscosity. This is simply the relationship that does this. And we wind up with this. We get a 4 because when we plug this value into here, we get 2 of these. So, and then we have a 2 here, so we get a 4 times that, times the viscosity, times the second derivative of the velocity in the x direction. That's equal to the gradient in potential energy. And obviously we can integrate that. We take that equation, we integrate it, and we get the gradient in the speed or the horizontal component of velocity here has moved this 4 eta nu to the other side, and we wind up with this simple expression where gamma is the value of the potential energy per unit area where x equals 0. And so, and remember, gravitational potential energy scales with surface height. It's not linear with surface height, but it increases with surface height. Gamma 0 provides a reference, so one has to make an assumption, and that's something we don't usually know, though we can turn and try to infer it, as I will show. And with the surface strain rates, whether they're compressive or extensional, will vary by this difference. Obviously, well, I'll say that. I'll get to that in a second. So the difference between these also, don't forget, the potential energy per unit area is at the force per unit length. So the gravitational potential energy that one has is a measure of the force per unit length. that a region at x applies to a region at x equals 0. So as an example, here's that same basic equation. This over here is a plot of potential energy. This line, the gray line, is potential energy as a function of x. X goes from the left to the right, increasing to the right-hand side. And here is an assumed value of the background gravitational potential energy, gamma 0, this value up in here. And I think it's clear, of course, if gamma 0 is greater than gamma x, as is the case over on the left side or over on the right side here, then because this is bigger than this quantity is less than 0. And so the velocities decrease as you go to the right. That means you're under compression. And conversely, if the gravitational potential energy over the region is greater than that, as it is in this middle part, would be the high region, of course. This is the gravitational potential energy. Where you're in this state, then you would have extension. The velocities would be increasing as you go away. And for this particular value, you have a plot of the horizontal component of velocity, which would be decreasing where the potential energy is low. So you'd be compressing this region. You'd be in this region where that value is bigger than that value. Then in this middle part in here, the potential energy of in these positions where x lies in this region between here and here is greater than the background potential energy. Then you'd be extending. You'd have extension in here. This is shown with this map view, extension in the middle, compression over here. And the velocities would be increasing as you go to the right. So you would have extension, and then you're back to compression. You can take this further and say, well, we could make the gravitational potential energy essentially 0 everywhere. In that case, of course, then you would have the velocities would increase everywhere across here, and you would have extension across the whole region, very, very minor extension in the green areas because the potential energy and the background potential energy are essentially the same. This condition we looked at, and in the case where the background potential energy were as high as you have in the highest region, where here gamma of x is equal to gamma 0, but in most of the region, gamma 0 is bigger than gamma x. In that case, where we would have this quantity be negative, in this case, then you'd be compressing all the way across here. You'd have the entire region would be under compression, though the compression in the middle would be negligible because the potential energy, there's no potential energy contrast in this region. So if you take data for the Apennines, this is now GPS data, points with error bars. These are velocities relative to the west side, southwest side, and they increase across, and they have 4 profiles, A, B, C, and D. I won't worry about where they are. But this suggests that the state is closer to this regime, certainly, than this regime. You're extending in the middle, you're extending where the velocities increase, and then the northeast side is moving away from the southwest side by this velocity, not very fast, only 3 millimeters a year. This is not rapid, but there's enough GPS data to define this. And so going back, east side, northeast, gravitational potential energy, and therefore on mean elevations. It's a very nice, simple pattern. So we can go to 2 dimensions, and 2 dimensions, then one has 2 of these equations that are alike. In one case, it's the x component, and in the other case, it's the y component. But think about this. We have horizontal gradients in the vertically averaged deviatoric stress. That's what the left side in each of these equations is, equal to the horizontal gradients in the gravitational potential energy per unit area, gravitational potential energy, or gamma, on the right side. This same we had for the Apennines, but now we go to 2 dimensions. Now, we can't measure stress, but we can measure strains or strain rates. And if we do, and we have a constitutive relation, so that if we have strain rates, we can infer stresses that scale with some viscosity coefficient. This quantity would be a viscosity. If n were 1, we would have Newtonian viscosity. E dot, which is the second invariant of the strain rate tensor, this quantity would become unimportant. 1 over 1 minus 1 is 0. And this would then would be 2 times the viscosity. Don't worry about that. We can measure strain rates with GPS or with geology, average strain rates over finite amounts of time. So in principle, we can get a number that scales with the stress, with the deviatoric stresses. So with measurements of strain rates, and by assuming a value of B, we can estimate the deviatoric stresses, and then we can estimate their gradients, and from their gradients, we can predict potential energy with a factor of B being wrong, but we can at least get a pattern. So if we look at a place like Asia, so this is Asia, Himalaya would follow along in here. The black bars are showing orientations of compressive strain rates. The white bars are showing extensional strain rates. So within the Tibetan Plateau in here, you have largely east-west extension, compression in the Himalaya, compression around the edges, compression in the Tian Shan. From geologic data, we can make estimates of strain rates in these elements that are drawn in here. And this is the Tarim Basin. Strain rates are very small. This behaves as a rigid object. Well, we can take those strain rates, convert them into stresses with some factor that we don't know, and we can integrate them and get an estimate of the gravitational potential energy. So the arrows are showing you the gradients in the strain rates. They're the values that are shown here. And the red contours are showing you the integrated value. If you take this and integrate and solve for gamma, you get the red lines. And the black arrows point perpendicular to the contours of the potential energy, because the gradients should be, the gradient and the potential energy should be given by these gradients. And the point to emphasize here is that the gravitational potential energy per unit area calculated in this way is high over the Tibetan Plateau, where it should be, because the Tibetan Plateau is high. There's more gravitational potential energy here than there is in the lowlands. And so to a first approximation, the thin viscous sheet does a quite good job of matching what we know. You can argue, well, what's this? Why do these bend around? Well, there are imperfections. It's not yet perfect by any means. But the point is that the gradients in the strain rates, which then lead to gradients in stresses, match the gradients in the potential energy, and the potential energy is high where it should be high. So if we look at this in a philosophical way, what's the essence of a good model? Well, ideally, only one free parameter governs the solutions. If you have a model with 10 free parameters, you'll never be able to know what's important and what isn't. You can't study it thoroughly. So when more than one parameter matters, equations should be rendered dimensionless. This is a philosophical point of view. Not all my colleagues share, but the people whom I respect, this is the view, because you want to get as few controlling parameters as possible, and non-dimensionalizing equations gets you there. Only a rare model presents results using dimensional parameters as good. I would argue you should be, if you're working with models, you should work dimensionless parameters. And the nice thing is the solution to the thin viscous sheet equations depends on only two dimensionless scaling parameters. There are only two that matter. One of them is the n in this relationship relating strain rate and the second invariant, the strain rate tensor, to the stress. One of the two dimensionless numbers we need to know is n. The other one is called the argon number. It's a big equation. I'll say more about this. But think of this as the ratio of the resistance imposed by gravity to the resistance due to viscosity. So you can see gravity G is in the numerator. The crustal density is in the numerator because it's the crust you're lifting. When you lift the surface of the Earth, you're lifting rock with a crustal density, and gravity is resisting it. It also has this relationship of 1 minus rho c over rho m, because when you push the MOHO down, the isostatic response has this relationship. If the crustal density is small, you must push the MOHO down. Takes more effort to push the MOHO down than if the crustal density is closer to the mantle density. So these numbers, all of these numbers, and this is the thickness of the lithosphere, again, this would enter into this. All of these numbers scale the resistance imposed by gravity. The bottom numbers scale the resistance due to viscosity. And in simple terms, this is the stress. One has a viscosity coefficient B. Well, there it is. The bigger B is, the more stress you get for a small amount of strain rate. So this is scaling stress. And then the product of these quantities is essentially a strain rate raised to the 1 over n power, right? E dot has the units of strain rate, epsilon dot ij has the units of strain rate. Well, you multiply them together, and what's left is this 1 over n. Well, to get something with units of strain rate, take a boundary condition velocity, V0, divide by some dimension like lithospheric thickness, and this has the units of strain rate, and it's a sensible quantity scaling strain rate. And so this whole product in here has a sensible scaling that's the resistance due to viscosity, the stress due to viscous processes. And so this is sometimes called the Feta-Brie number, because the argon number, if you have a large argon number, it means gravity is important. And think of brie, or if you prefer, camembert cheese, because it flows. The gravity overcomes the weak constitutive relationship of the cheese itself. Brie oozes out. And a small argon number, which you can make small by either making G small or making B large, for example. Think of feta cheese. Feta cheese comes in blocks, it comes in bricks. And gravity doesn't deform feta cheese, it just stands there. So we nickname the argon number as Feta-Brie, and this makes it easier to remember in some ways if you know the cheeses, the French cheeses, and well, feta is a Greek cheese, brie is a French cheese. So here are some numerical calculations that Hausmann and England, these are the two of the leading people in this work, where calculations with argon number 0, 1, and 3. And what they've done is they've taken a sheet, a thin viscous sheet, and indented it. So this black is the indentation in all cases, the same amount. And what they're plotting here is the crustal thickness that they calculate from this. Crustal thickness is localized right near this surface when the argon number is 0. Well, when the argon number is 0, gravity isn't resisting at all. All the resistance is due to the strength of the material. If you increase the argon number, okay, then you make gravity more important and the deformation spreads out. These contours move farther apart, and there's localized deformation near the corners because of the corners, but not localized all the way across. And when you make the argon number even bigger, the deformation spreads out further. And this makes sense if you think about it. If you have a substance that's low viscosity, it will spread out. But if it's high viscosity, it will spread out very slowly, and hence will give you steeper slopes. So steeper slopes with a small argon number, and gentler slopes with larger argon number. And the same is true if you change the value of n in this relationship. If you have a value of n equal 10, you'll have much more localized deformation. Actually, we talked about this a few weeks ago. Much more localized deformation in this case than when the value of n is smaller, as in the case where n is equal to 3. The deformation is spread out much more with this number. And so if we take and apply this to Asia, where what they've done is they've put a boundary that looks a bit like the northern edge of India, as I've shown you here, the northern edge across like this, and everything is oriented not north-south, but would be north, northeast, south, southwest. In one case, with a very large value of n, but a reasonable value of the argon number, you have localized deformation, largely because n is large. The argon number would spread it out. But if you make n smaller, but let the argon number be smaller, again, you have localized deformation. So in this case, the deformation is localized because gravity provides no resistance. In this case, gravity is providing resistance, but the n is so large, it's localized. And if one looks at the hypsometry of Asia, this is now a plot. The area above some height of 1 kilometer, 2 kilometers, 3, 4, 5, 6, 7, 8 kilometers. Mount Everest would be out here above 8 kilometers. There are 14 peaks above 8 kilometers. And this is surface height going across here. First, the data are the black line, the continuous black line that comes down through here, goes up and around in this area. If you have the argon number equals 0, gravity is not important, then you can have very high elevations. This is the case, argon number is 0, and n is 3. You can have very high elevations because gravity is not resisting the building of high terrain. It's the only thing stopping building high terrain is the viscous material, the viscosity of the material. At the opposite extreme, when the argon number is very large, 10, that's this curve coming down through that black circle to that black circle, you have almost no terrain that's higher than 2 or 3 kilometers. And the reason is simple. The material spreads out. As you try to deform, instead of building narrow mountain ranges, it just spreads out. It flows away from you. And England and Hausmann, use this to argue for argon numbers in the range of 1 to 3 and n in the range of 3. N in the range of 3, recall, is typical for deformation of minerals like olivine or quartz. Okay, well, another test. If the thin viscous sheet describes deformation of continental lithosphere well, then the straining of the upper crust should match that of the upper mantle. They both should strain together. And we can constrain surface strains geologically or strain rates geodetically with GPS. And we can use seismic anisotropy to address finite strain in the mantle. So a comparison provides a test. And let's look at the picture on the right, going back some time ago. This again, we're looking in Asia, so you can't see this well. This is Nepal, this is Bhutan. So this part of this map is this part of this map over here. And they've calculated finite strain ellipse by indenting Asia with a thin viscous sheet. And so the maximum elongation is what? West-northwest, east-southeast up here. Very marked elongation here, less so, less strain in here. And these bars are showing you the orientation of the fast quasi-S waves. These bars should be parallel to the maximum elongation. And it's not bad. It could be better. It's quite close in here. It's very nice when you get where the strains are large over in here. The one on the left is showing you a bit more data. So the red and the blue are observations. Again, some of these observations are the same. That one is the same as that. And this one is the same as this. Note, this is quite old. And the black lines in the background are showing you the orientation that you would expect for the fast quasi-S wave if the present day strain rates evolved long enough to deform this. There's more data since this, 10 years later or so. On the left are shown the orientations of fast quasi-S waves. So fast orientations that swing around, they're east-west up in here, swing around, become more north-south in here, but then become east-west in this area. And plotted on the right are the combination of these, the splitting measurements that are underneath them and the calculated orientations that one would get from the present-day strain rates, assuming the present-day strain rates operated for a long enough time to induce anisotropy. And you can see this is really a very, very good fit. Everything is lined up, not everything. Most of these are lined up pretty well. There are a couple in here that don't fit. And even these down at the bottom, you'll see these are oriented east-west. Everything is north-south and suddenly east-west. And the logic here is very simple. Here you're shearing in a strike-slip sense to align these, as we talked about in New Zealand. But down in this region, you have divergence. This region is going to the south, this region is going to the southwest. This is going to the southeast. And so you're stretching in an east-west sense. You're stretching here. And again, the maximum elongation is stretched across here with this east-west extension. And so the point is that the seismic anisotropy really is a nice confirmation that the thin viscous sheet is working. The strain rates and strains at the top look like what one infers from seismic anisotropy. So virtues of the thin viscous sheet: it combines two sources of resistance, the forces per unit length that do work against the strength of rock and against gravity. This is the potential energy part of it. This is friction or viscosity. Only two non-dimensional numbers, n and the argon number, plus boundary conditions, of course, dictate the form of the solution. And this allows it to be studied quite thoroughly and therefore understood. And it's easily extended to allow consideration of lateral variations in the viscosity coefficient. I'll show you that in a second, because one can change the value of B throughout the region and in fact try to infer that. And it works in the sense that it helps us to understand the relationships among velocities and strain rates measured with GPS or geologic techniques, rotations, because rotations are important, using paleomagnetism, and strains based on seismic anisotropy. It brings all of these quantities together. So I mentioned you can actually study lateral variations in the viscosity coefficient. And so the arrows here are showing the orientations of stresses, in quotes, because we haven't quantified those stresses, but just as one scales with strain rates. So one has extension in here, one has compression along the Himalaya in here, compression across these regions. One might have stress in here, but one doesn't have much strain in here. And what Lucy Flesch and her colleagues did was solve for the viscosity. And here's a scale, and these numbers might not mean very much to you, but this is a high viscosity and this is a quite low viscosity, assuming Newtonian viscosity. And the Tarim Basin indeed has a high viscosity, and Tibet in here indeed has a low viscosity. So Tibet is soft. We think we know this. It's hot. The crust is thick, but it's not a strong region, whereas the Tarim Basin is strong. The Tian Shan come through here, but then one goes into a strong region, and northeast China up in here is also quite strong. They haven't solved for India. India is an indenter, and it's not part of what they're doing. And they can take this further and say, well, what happens if we allow n to be 3? So we're now solving for B. It's different units. Let's not worry about it. But once again, the Tarim Basin comes out strong, and Tibet strong by being a cool color, and the Tibetan Plateau comes out weak, being a hot color in here, low viscosity. So the thin viscous sheet gives us, or it can be used to solve for lateral variations in strength. So I'm going to go back and take some other simpler examples. This is a very nice piece of work looking at Anatolia and the Aegean. So the Black Sea is up here. This is the Anatolian Peninsula, if you like. This is Turkey. And these are fault plane solutions of earthquakes. And this is the GPS velocity field relative to Eurasia up in here. And you see this westward movement and then swinging across and overthrusting along the Aegean arc in here. And you can't see it, but there's extensional strain in this region. If one takes the mean elevations, so that's high, maybe I should back up. This area is high. This area is lower. That's below sea level, even lower still. If one takes the elevation, smooths them, one gets the potential energy. This is the potential energy, GPE. high potential energy where the region is high, low where you're below sea level, and then just takes this with the thin viscous sheet equations and calculates what velocity field you'd expect. And it's hard on a plot like this, where that's 40 millimeters a year, to see the difference between the calculated and the observed. If you take the difference, and I think M is some measure of misfit, but the green show regions where the misfits are smaller than 3 millimeters per year. And so some are bigger, some are a little bigger. And this is what you get if you assume n equals 3. This is what you get if you assume n equals 9, and they're really not very different. But that's the only parameter they're playing with. And they can do a little better if they allow the boundaries to move. They play with the boundaries over here. They can get a somewhat better fit. This is the best, the smallest misfit that they get by allowing the boundaries to move. But I emphasize that they've used only one parameter. This is a good test. Why? The model, the thin viscous sheet, relies on only one free parameter, the n in the power law. They know the potential energy because they know the elevations and they assume isostasy. So the relationship between strain rate and stress, that's the only thing. Now, the weakness is they don't really constrain n very well. But never mind. They get an effective viscosity of the deforming region in this 10 to the 21, 10 to the 22 Pascal seconds. But the point really is only one number is free, and it really doesn't matter. Essentially, they can explain everything without making assumptions other than isostatic equilibrium and the thin viscous sheet equations. And another example for Iran and surrounding regions shown over here. Again, arrows showing the velocities that are measured with GPS relative to Eurasia. Fault plane solutions of earthquakes. The blue ones are all showing thrust faulting around the margins. And they can calculate gravitational potential energy in two ways, actually. They can calculate it from the topography, assuming isostasy, or from the geoid. The geoid itself, the gravitational field expressed as a geoid, will get you an estimate. And you can see they agree quite well with one another. It doesn't matter which of these two you use. And when they solve, again, the white arrows are the observations, the blue arrows are the calculated values, and they're not very different. They differ a little bit in places. This is the misfit, again, with the green showing you the ones that are misfitting by some small amount, and the red showing ones that misfit by more. So there are some that are not fitting that well, but it's a pretty good match when you look at it shown in this way. So once again, why is this a good test? Same reason as before. The model, the thin viscous sheet, relies on one free parameter, n, in the power law relationship between strain rate and stress, although again, n is not tightly constrained, and the effective viscosity is not pretty tightly constrained in this simple way. Well, I want to change direction a little bit and say that often we learn more when models fail, when both simple or complicated models, when they fail to match the data, than when they succeed. And let me take you back to Tibet. This is Tibet, the Tibetan Plateau, and you have normal faulting throughout the Tibetan Plateau. These symbols show you fault plane solutions of earthquakes within Tibet, and the blue are showing normal faulting. And throughout the high plateau, you have normal faulting and east-west extension. Thrust faulting occurs on the surrounding flanks. Thrust faulting in the Himalaya, thrust faulting up here, Qilianshan, and out here just north of the Kunlun. And crustal thinning occurs throughout Tibet because normal faulting requires crustal thinning. Crustal thickening occurs on the surrounding flanks. Well, the thin viscous sheet parameterized by n and argon, the argon number alone, fails to give us normal faulting, crustal thinning, and east-west extension. It simply doesn't give us this. This is this strain rate field that we've gotten. This is topography. And the black arrows are showing you the orientation of compressive strain. And you've got north-south compressive strain, but no extension, no east-west extension at all, not even a hint. And whether you have an argon number of 1 or 2, whatever your n is, you have this same pattern. You simply don't get this pattern. So why? And what this is work of England and Hausman. What they argue is, what can you do? How can you change things? Well, you could make the Tibetan Plateau weaker. We know the Tibetan Plateau is weak, but if you weaken the Tibetan Plateau and you have the same boundary conditions, in fact, you won't create normal faulting and extension. You'll create increased crustal thickening. You'll make more thrust faulting. So this simply won't work. That doesn't help. You could get a balance between the north-south compression and the vertical normal stress, but this doesn't work because then you wind up with conjugate strike slip faulting and no crustal thinning. Their solution is to raise the surface of Tibet and thereby increase the gravitational potential energy and increase the vertical normal stress, and this will give you east-west extension. It may enhance north-south extension, but if you have a strong enough north-northeast, south-southwest compression, you won't get extension with that orientation, just the east-west extension. And they did this. When they removed mantle lithosphere in the thin viscous sheet, they got crustal thinning in this region. This worked. And as I said, the key here is that that the model didn't work. Then they learned more in many ways from finding a situation where the model failed than finding a situation where the model succeeded. And this is going to lead me to what I plan to talk about next week. But anyway, removal of mantle lithosphere is the key. Removal of the mantle lithosphere gave the potential energy per unit area in the remaining lithosphere of Tibet. It increased that potential energy, and that caused the plateau to spread apart. So some of you surely think that I'm on dangerous footing. I'm using this for a reason you'll see in a second. With removal of mantle lithosphere, surface uplift, and a switch from horizontal compression to horizontal extension. And so I just want to give you a little bit of dangerous footing. This is a photograph looking across to Afghanistan. That's a trail. And here's a blow up of the trail. This is the part where the trail just goes in here. And I would describe this as dangerous footing. But this is the other side. This is Afghanistan. I took this photograph from the Tajik side of things. So to summarize, I'm early, but that's okay. To summarize, with the thin viscous sheet, a balance of gradients of stresses with gradients of gravitational potential energy in a thin viscous sheet accounts for a large-scale continental deformation. The key here is that one can include two resistances to deformation, stresses or viscous processes, and gravity. Gravity, of course, is resisting the building of high terrain. The thin viscous sheet allows us to do this. In general, though it failed with Tibet, only two parameters are needed: the Argon number, which scales the gravitational resistance to the viscous resistance, and N, which relates stress to strain rate. Just two parameters. This is elegantly simple. The agreement of present-day strain rates and finite strain in the upper crust with orientations of anisotropy in the upper mantle provides a test of this idea. If we're assuming that the lithosphere is behaving as a sheet in a gravitational field, a gravity field that resists its thickening, the fact that the surface strain rates and the finite strain that one observes in the mantle with seismic anisotropy agree, the agreement of those two quantities is really a very strong confirmation that the thin viscous sheet works well on this scale of hundreds of kilometers. And then to come back, only two parameters are needed, well, except for failure in Tibet. But the point is, failure is good, because when we fail, we learn. And what we learned from this was the importance of removing mantle lithosphere from beneath the Tibetan plateau. And so this is my last slide. I hope I didn't go too fast because I finished plenty early. So over to you, Hector. Hector, are you there?
Yes, I am here.
I'm sorry, I can't see anything except my own screen, so I can't be sure if you're still there.
Okay, thank you very much. There is a question, Pete. How does the gravitational potential energy vary with rocks of elastic and ductive behavior?
It shouldn't. It shouldn't depend on those properties. The gravitational potential energy depends solely on density and gravity. It's the integral of the lithostatic pressure, and lithostatic pressure is simply the weight per unit area of the rock above. So in principle, there'll be no dependence of gravitational potential energy on viscosity or frictional properties. Now, of course, if you had very low viscosity material, it would be hard to maintain large gravitational potential energy because the high regions would flow apart and sink down to low elevations. But the gravitational potential energy itself does not depend on the viscous processes. The response will depend on the viscous processes.
Okay. So far, there are no more questions, Pete.
Okay.
Ok. Entonces, muchas gracias a todos por su atención. Nos vemos dentro de una semana. Thank you, Pete.
Thank you. I hope I didn't go fast. I hope I was clear.